All right. It is 12:30 p.m. on September 12th. And I'm going to go ahead and start today's lecture and talk a little bit about topic of the lab and address some of as I go through, I'm going to address some of the struggles that you guys had that I saw pop up on the discussion board over and over. On that note, if you did post something on the discussion board, be sure to double check that I didn't make a comment on your discussion post asking you to revise one of your questions. If I did ask you, like, hey, can you reply with, a fix to whatever it is that I asked about? That's because I want you to make that fix to earn all of the points total. If you don't make that fix, then there will probably be a point deduction. So just be aware of that. Um, all right, so let me pull up. We'll start off today with a PowerPoint, and hopefully on screen you'll be able to see, yep, you'll be able to see the word measurement and motion. That's what we'll be talking about today. While I'm at it, I am going to pull up chat log and participants to keep an eye and see who joins us and if questions pop up. All right, so let's jump into it. So I wanted to start today's PowerPoint discussion, sort of revisiting, refreshing an idea that we were talking about last time, and this idea of measurements. I want to reiterate the importance of the two parts of a measurement. So measurements have numbers, and I think we all get that. I think we all have this understanding that measurements need a number. But also really important is a unit. A unit tells us about this measurement and tells us specifically about what this measurement is measuring, right? What it is trying to tell us, right? So if we have something that is measured 32 feet, we can infer upon what that measurement is. It's a measurement of length, it's a distance. It tells us something about how far maybe two things are separated from. And that comes with that unit that's very different than saying something is 32 kilograms, right? Because that's telling you, well, that's how massive an object is, right? It doesn't tell you about length, it tells you about mass. And last time we were talking about unit conversions dealing with density, right? We talked about two different units of density, one a gram per centimeter cubed and kilogram per meter cubed. These are two measurements of density that tell you about the same physical quantity. It tells you about, how essentially tightly packed matter is into a region. But, kilogram per meter cubed, centimeter per gram cubed, or sorry, gram per centimeter cubed, kilogram per meter cubed. Like these are both measurements of density, the same physical quantity, but there are two different ways to look at it. Just like at length, you can look at it with feet, you can look at it as inches. These are two different measurements that might represent the same thing, right? Both a length. So a couple of examples that we have here. Same examples as last time, right? Class is about an hour long. You have the number part of this. One, again, we all did a great job last time of finding those numerical values of density. But some of us left off the unit, right? So we need to have that unit because saying class is 1 hour long is a lot different than saying class is 1 minute long, right? Those are two very different measurements of time. So it's important to be specific about what that measurement is. Now we can do unit conversions, right? We can say class is 1 hour long, class is 60 minutes long, and that's telling you it's the same amount of time, right? Because 1 hour is 60 minutes. But it's important to have that unit because if I say class is 60 hours long, well, then that's really long class, and that's probably not right. So we have to match the right number to the right unit and make sure we have the same values there. We also have an example. I gave this one as well last time. I drove 25 miles to work. It tells you the distance you had to travel. 25 is the number, miles is the unit. 25 miles is a lot different than 25 feet. I wish I worked 25 feet away from work. I just get up in the morning, walk to work. But no, I had to drive about 25 miles. And then for those of you that are curious, it's actually not 25 miles, given this as a random example. But the point still holds that this measurement of distance, it needs a unit attached to this number. We cannot forget the unit. If you forget the unit, I'm going to ask you, well, what about the unit? And for a few of you in your discussion boards, I did ask you to include the units. All right. Last example, I weigh about 210 pounds, right? 210, the number, pounds is the unit. So we have this idea that every measurement, it needs a number and a unit. We cannot forget the unit. Now, it's all well and good. I had a few people asking about unit conversions, right? So they were still a little fuzzy on unit conversions. So we'll go through an example. And last time I gave the example of height, I'm going to do the same thing again. And I like giving this example because it has kind of a weird conversion factor, right? It's not power of 10 like all of our SI unit conversions like we learned last time. Feet to inches, it's a little bit different, right? Because what we know is 12 inches is 1 feet. So if you have a student that is 5'8" tall, let's say this student wants to know how tall they are in inches. Well, we then need to apply this unit conversion to get the feet to inches. Now, what this is saying is actually that we have 5 feet plus 8 inches. So when we look at this, we know we need to convert to inches, but we only have to convert one of these numbers. We only have to convert the 5 feet to inches, right? And once we have that 5 feet, we'll add it to the 8 inches to get the total height in inches. So we start by writing out, what is the relationship here between inches and feet? We write out 12 inches is 1 foot, and we create a unit conversion factor. This unit conversion factor, oh my gosh, hold on. This unit conversion factor for us is going to be that 12 inches is 1 foot. We take the 1 foot and we divide over to the other side, just doing a little bit of algebra, divide both sides by 1 foot. And on the right-hand side, you have 1 foot divided by 1 foot. Well, when you take the same thing and divide it by itself, that is by definition a value of 1. So whatever this thing is on the left-hand side, we know that it equals 1, the numerical value of 1, and that's very important that it equals that numerical value of 1. And then on the left-hand side, we just have 12 inches divided by 1 foot, right? So this is our conversion factor, we would call 12 inches divided by 1 foot. And our conversion factors should always be equal to 1. And they need to be equal to 1 because when we take our measurements, and we, there we go. When we take our measurement and we multiply it by the conversion factor, in this case 12 inches divided by 1 feet, when you take your unit conversion multiplied by that factor, that is just saying you're taking your measurement 5 feet and you're multiplying it by 1. And by multiplying it by 1, we don't change what this actual measurement is. It stays the same measurement. It stays the same thing because you take anything, you multiply it by 1, it does not change the actual value of that thing. So by taking 5 feet, multiplying it by the unit conversion factor, we are not changing the measurement. We are simply changing the way that it looks. And when we do this unit conversion, what we can do is combine together the numeric parts, the 5, the 12, and the 1, and the unit part, and just kind of rearrange them. Remember, everything's multiplication division here, so we have the freedom to move things around as we see fit. We just need to make sure that what's on the top of fraction stays on the top, what's on the bottom stays on the bottom of fraction. So we have the 1 from the 1 foot going down here, unit there. We have the inches going there, we have the feet going there, we have the 5 and the 12. So all of the pieces here are accounted for. And what do we get when we have this? We have 5 times 12 times 1, that gives you 60. So the numeric part comes out to 60. Feet cancel out, we're left with inches. So 5 feet is 60 inches. And this is probably a fact that we're pretty familiar with. If you grew up in this country and use these like measurements of feet and inches, you're probably familiar with the idea that 5 feet is 60 inches. But that wasn't the height of the student, right? The height of the student was 5 foot plus 8 inches. So we add to that to get that the height of the student is 68 inches. And this is just one example of a conversion, right? Very similar to the one we did last week, but I do that because I think repetition helps, and that seeing this a second time, well, if you're seeing this for the second time, then you're probably gaining a better idea of what I mean when I say things like conversion factoring. If I say conversion factor, your mind should think, oh, that's the thing that equals one that we multiply our unit by to change the units. That gives you your values. Okay. So we have this idea of unit conversions, and that's wonderful. I want to reiterate some things about the SI unit system, and yeah, this is a lot of the similar stuff. Oh, let me clear my annotations. All right, there we go. So we have this idea of unit conversions, and we define this SI system to aid us in our unit conversions, because with this SI unit system, the conversions actually become quite easy. They're just multiplication divisions by things like 10, 100, 1,000, and ultimately that's just moving the decimal point over. So we have this SI system that we define. Now I want to reiterate this because there are a couple other places where I saw students saying a little bit of not correct ideas. They're kind of hinting at ideas. And I just want to reiterate something about this SI system. Now, we have two measuring systems that are commonly used in the world, the SI system and the imperial system. In the United States, we tend to use imperial system in our day-to-day life. That is values like pounds and feet and inches. Um, in most of the world, though, they stick to this SI system. Now, this SI system was created during the time of the French Revolution, and during this time it was created because merchants needed an easier way to do math to deal with their trade. So we define these in order to make the math a little bit easier for the people that are performing trade. And uh, in the discussion board post from last week, I had asked you to think about, to consider why it is that it's more common to use kilograms than grams when grams is the base unit in SI system, although we don't often treat it like the base unit. And I had a few people saying, oh, grams are SI system, kilograms are imperial system. That is not quite correct. It's correct to say that both grams and kilograms are part of the SI system. They're just different depending on what we call their SI prefix. And their SI prefix doesn't change the fact that they're in the SI system. Their SI prefix does still maintain that they are in the SI system. It's just looking at a different value. So um, in the case of the discussion post, when I was talking about this idea of kilo K grams, combining those things together. Well, what that does is it says a kilogram is a unit of measurement that is 1,000 times larger than the base SI unit. So you would say 1 kilogram is 1,000 grams. And again, they're both part of the same SI system. Neither of these are imperial, neither of these are metric. They're both part of the same SI unit system, but one of them is more useful in day-to-day life, and that would be the kilogram. So a gram is a very, very, very small amount of mass. It's a small amount of mass to the point where it's not going to show up very often. Excuse me. So it's not going to show up very often because most things are done on this scale of kilograms. So we just adopt kilogram as the more commonly used unit. And for physics, we do actually tend to talk about kilogram as being the basic unit, the base SI unit of mass, not necessarily the gram, because again, kilogram is much more useful. It's much more useful and reasonable to use on a day-to-day basis. All right. Clear my annotations. All right. So I say we use the SI unit because it's easier to do conversions. And we'll do a couple of conversions here. And these are meant to pop up one at a time. They weren't meant to all pop up at the same time. And I already see a typo that I made in the screen. But we'll walk through these unit conversions right now. So you might be asked how many centimeters is in 2.5. That was supposed to say 2.5 meters, not centimeters. How many centimeters are in 2.5 meters? Well, to do that, you create a conversion factor. In this case, we would say 100 centimeters is equal to 1 meter. And I do apologize for my handwriting. I'm still using a mouse. I haven't managed to get my little stylus and trackpad working yet. But we have 100 centimeters is 1 meter. We take this, did not need to do that. We take this value and we create a conversion factor, in this case, 100 centimeters divided by 1 meter. So combining the numeric parts, what's 2.5 times 100? This is a quick calculation to do, right? Multiplying by 10 is a lot easier than multiplying by 12, or in this case, multiplying by 100, which is 10 times 10. It's a lot easier than like multiplying by 12. So there's an advantage to doing these SI units instead of using imperial units, in that the multiplication is a lot easier. You can take 2.5 multiplied by 100 divided by 1, and you would get not 350, but 250. And then the units, well, meters will cancel out with meters, and you're left with centimeters. So to convert from centimeters to meters, all you do is, or convert from meters to centimeters in this case, all you have to do is multiply by 100. That's an easy mathematical operation, right? You just move the decimal point over 2 times. How many kilograms is in 360 grams is the next one. Well, 360 grams, we create the conversion factor that comes from 1,000 grams. 1,000 grams is 1 kilogram. Kilo means 1,000. So we have 1,000 grams is 1 kilogram. So we take 360, we divide by 1,000, and we get 0.36. Our units, well, one of our grams cancels out, we're left with kilograms. So our and the answer to the question is 0.36 kilograms is the same measurement as 360 grams. This is equivalent to saying, 2 hours is 120 minutes. They're both the measurement of the same thing. 120 minutes is the same exact thing as 2 hours. Well, in this case, 0.36 kilograms is the same thing as 360 kilograms. So we have these conversion factors that come from the SI unit, and these are designed, the SI units are designed so that the actual mathematics that you do is supposed to be pretty easy, pretty straightforward, just multiplying, dividing by hundreds of thousands. Now, you got to keep track of things, keep track of if you're multiplying or dividing by 1,000. That's where creating these conversion factors, these 100 centimeters over 1 meter, 1,000 grams is 1 kilogram. That's where creating these conversion factors are important. And it does take practice. It's going to take you some practice. But as you go throughout this class, you'll get more and more comfortable with the idea of these unit conversions. So all of that's recap. All of that's recap from last time we were here, right? Last time we were discussing these ideas of unit conversions. I want to get into new stuff now. And the new stuff is going to be based on, the ideas of the lab. So what exactly are we doing? Yes, there's going to be a unit conversion for you to deal with this week. But what is the lab about? And the lab is about this idea of motion. When we talk about motion, you might be looking at an object that undergoes some change in position, right? So we might say that this is the starting location of an object. Now, when you talk about motion, you're saying that that object, whatever it is, maybe this is you and me moving throughout some walk. You have this object that has some starting point, and it is going to move. So we have an object that is going to be at the starting place. I'm sorry, I just got an important text message that I needed to make sure was fine. So you have an object that has some starting location, and it is going to move along some path. In this case, our object will start at this top left location. What's it going to do? Well, it's going to move along these arrows. It's going to move 4 meters to the right to this location, 2 meters down to this third location, 4 meters to the left to this location, then 2 meters back up. And we might want to analyze the motion of whatever it is undergoing this path that goes from top left to top right to bottom left and back to its original position. Well, to do this, we in physics tend to talk about two different physical quantities. One of these physical quantities is distance. And distance is a description essentially of how much ground an object has covered, how much ground has it passed as it moved throughout its motion. We look at this and we say, well, it moved 4 meters and then 2 meters. So that gives you 6 meters, and then another 4 meters. That's going to give you 10. And then 2 meters more, that gives you 12. So you look at this and you say, well, it's clear the object moved 12 meters. Well, what is that a description of? That 12 meters is a description of how much distance the object has moved. Distance is not always the thing we talk about in physics, though, because often what we care about is displacement. We don't always care about the exact path an object takes. What we care about is how far out of place that object is, or how far away from its initial position it might be, or some variation on that. So with displacement, we're asking the question, how far out of place is the object? And this introduces some weirdness that'll come up. For example, on this path that we were just talking about, I'm going to outline in red starting point. This dot represents the starting point, okay? We look as it goes throughout its motion, it's going to move right and then down and then left and then back up, and then it ends where that green circle is. And we might say, well, how far out of place is the object? The object started at top left at the red dot, it moved throughout its green path, it ends at that green circle. It is in the exact same place that it started. How far out of place is it? Well, it's exactly in place. So in this case, it's 0 meters away from where it began. It's 0 meters out of place. So we would say that the distance traveled is 12 meters. However, the displacement is 0 meters, and that's perfectly fine. It's okay to have something that has 0 meters of displacement. That doesn't mean it didn't move, it just means it's exactly where it began. If you think about your day as you go throughout the day, you start at your home, you start out in your bed, you get up, you go to work, you travel maybe 12 miles to get to work, you work, and then you travel maybe 4 miles to go get dinner, and then another 8 miles to get back home, right? And you calculate, well, how much distance did I cover in the day? Well, you definitely moved. You look at your car's odometer, and it'd be what, 24 miles higher up than it was when you started the day. So you moved a distance of 24 miles. But your displacement, well, you ended up right back at home. You end up in the same place that you started your day. If that is the case, then your displacement is 0. Again, it doesn't mean you didn't move. It just means that you ended up at the exact same place that you started. And that's the difference between distance and displacement. And we'll be using these ideas of distance and displacement throughout physics. And you'll be using this in your lecture over and over, this idea of distance and displacement. Now, what's interesting is that in physics, it is often displacement that is of concern. There's often displacement that is of concern because it tells you about the whole trip without having to deal with the intermediate path. And a lot of physics ends up being, we say, path independent. We don't really mind whatever path it takes to get from start to end. We just care about, where does it start? Where does it end? Clearing annotations. We move forward and we ask the question, okay, well, we have this idea of distance and displacement. Distance tells you about how far you've moved. Displacement tells you about How far out of place are you, meaning, how far overall did you move? But these tell you only part of the story. It doesn't tell you anything about how quickly the motion happened, right? This motion could have happened very quickly if you were running these paths, or it could have been very slow if we're tracking a snail as it moved through these paths, right? So we might be concerned with this idea of how quickly this motion happened, and how quickly this motion happened is a description of what we call perhaps speed. There's another term that we use for this. We'll stick with speed for right now. And what speed tells you is a change in position over 1 second, right? So that's how we typically define speed. Well, kind of. We'll get more mathematical about it soon. But for right now, it's good enough to say change in position over 1 second. And we can track a particle's motion. Perhaps we track a particle's motion where we see how far it's moved every second. We say, okay, object starts at one point, and then after 1 second, it will have moved 6 meters. After another second, it will move 12 meters, and it continues to move further and further, right? So we can say, well, what is true about this? Well, it's moving 6 meters every second, right? We start at 0, we go 6 meters in the first second. Between the first and second, we travel from 6 to 12 meters. So that's a change in 6. Yeah, we're at a total of 12 meters now. But during the previous second, we've only moved 6 meters, right? And then we have another 6 meters and then another 6 meters. So we have this idea of a change in position over some amount of time. And that tells us about our speed. Here we would say that we move a total of 6 meters every second. So we have this idea of speed and position. That's primarily what our lab is going to be focused on today. All right, so we're going to be focused on this idea of speed and position. Now, with our lab, we are going to be representing speed first through this idea of what we call ticker tapes, and ticker tapes are one way for us to sort of track our motion. And I want to give you an idea of where this sort of name comes from. I got to clear my annotations again. So with these idea of ticker tapes, well, they come from this device called a ticker timer. And I want to show you a video of how this works. And I'll talk through this video as it proceeds. Let me just, there we go. And of course, we have an ad first. Okay. So this is a ticker tape analysis. It's an analysis of motion using this device called a ticker timer. And that's what you're seeing on screen right now. It's essentially a little black box. And what this will do is it will make a marking on a tape roll, and that's the ticker tape roll. It'll make a marking on this at regular intervals. In this case, probably 1/10 of a second. And you can use this to analyze motion, and this video uses it to analyze the motion of a little toy car. And you'll see that the person setting up the experiment feeds the ticker tape through the ticker timer so that the markings get made on the ticker tape, and tapes it to the car, and then the car will be sent off, and every 1/10 of a second or so, we'll have a marking made. And that's what you see here is markings on the ticker tape made every couple seconds. Now, in this case, in the case of that little cart that we just saw, you'll see that the ticker tape is evenly spaced out. And with this even spacing, we can do a little bit of an analysis. We can look at neighboring dots. Oh, it's not letting me annotate. Let me see. There we go. All right, so you can see that the dots are separated by some distance. And what we can do is we can look at how much distance is between dots and set that take that distance and divide it by how much time happens between dots, and we get an idea of the speed. And with this ticker tape, we can get several different types of motion regarded. Oh my gosh, sorry, my annotation is all weird. There we go. All right, now with this ticker tape, we can get several different representations of motion. Those different representation of motion might tell us different qualities of what is going on as the object moves. For example, you might have tape that has the dots very far apart on the tape, or you might have them very close together, or you might get cases where the dots start close together and as time progresses, get further and further apart. So you get different representations on the ticker tape, and this tells you something about speed. And specifically, we think about speed, and going back to what I was saying earlier, speed is all about how much distance is covered in time, right? So if something covers more distance in a given time, well, that means it is traveling faster. So we look at this top tape, and this top tape has a very large distance between us. That tells us something about its speed when we compare it to something where the distance is a little bit smaller. And we can even gain some understanding of what's going on with speed if the distance is separate. So I'm going to put up a slide that has a few examples of what you might see with ticker tape. You might see examples where we have them very far spread apart. This means it is covering a large distance in the amount of time that it takes for the car to travel. Well, if the dots are more spread out, it's covering a long distance with time. That indicates that we have an object that is fast. So if the dots are very far spread out, that's saying that the object is moving quite quickly. However, if the objects are close together, well, this is the converse of that, right? The converse is that if dots are spread apart means fast. If they're close together, that means that the object is probably traveling slowly. So you have slow object covering small distances in time. And that's why the dots are close together, or fast object covering large distances. That's why the dots are more spread apart. You might have an object where the dots are close together and spreading apart. Or you might have the object create dots at regular intervals. In the case where we have regular intervals, well, that means every moment of time it is covering the same amount of distance. We call that constant speed because it's not speeding up, it's not slowing down. If it's speeding up, well, speeding up is indicated by the dots going from quite close together, meaning we're traveling slow to begin with, to the dots being spread further apart later on. That means that the object has gone from traveling slowly to traveling quite quickly. And we would call that type of motion acceleration. This is the term we use for changing speed. And the more dramatic the acceleration, the more these objects will have their dots spread out. We'd have lots of acceleration if they spread out quite quickly. Now, we'll talk about acceleration more next. The next lab is dealing more with acceleration. I want to take a pause here and show you. Oh, there are my annotations again. All right. So I wanted to take a pause here and show you this activity that we're doing today and the first part of the activity, and then we'll go back to the PowerPoint and discuss a little bit more. So first part of the activity, well, it has a question in here that deals with, we have a question in here that deals with unit conversion. So checking in with you, how are your unit conversions going? Again, I know a lot of us said we struggled with unit conversions when it came to the first exercise. So I want to refresh you a little bit and give you a brief rundown. And at the beginning of lecture today, I gave another brief rundown, and I'll happily talk about it a little bit later on again as far as unit conversions go. But the first part just asks you, okay, let's check in. Let's see if we can do a unit conversion. You'll be given a randomized number, in my case, 6.4 centimeters, and asked, okay, convert that to inches. Um, then we move on to the idea of displacement and distance traveled. For this, remember the difference between distance and displacement. I talked about that at the start of lecture, but the difference is that distance is the total amount of ground that was covered, whereas displacement is just the change in your location from start to end. So being careful about analyzing the motion. We start at point A, our next point is B, and then we go back to the left to C, and then back to the right to D. So we do have displacement happening, causing a change. We do have distance traveling and displacement. Those are two different values in this case, so being careful with that. And then we get to the part that deals with the sort of ticker tape-like behavior. So we start analyzing motion, and we're analyzing motion on these videos that we have presented for us. In this case, this video for today is a ping pong ball being shot at a cannon, and you'll see it happens quite quickly. Well, how are you going to analyze it? You're going to analyze it with the tools that allow you to make markings on the video itself. So when we look at the video, we can make a marking, on this frame, this is where the dot is. And then we can proceed forward to the next frame and then put another dot down. And what this does is it creates a line of dots. If you look down here on the bottom right of the screen, creates a line of dots that look a lot like those ticker tape behaviors. And in fact, this is exactly like those ticker tape behaviors, where it makes a mark every given amount of time, in this case, every single frame. And you can figure out how much time has passed with that little timer tool. So it gives you an opportunity here to make those ticker tape timing diagrams for yourself. And then you analyze the motion based on it. Like it asks you, what did it look most like, right? Did it look like it had large spacings and then got small, or did it have regularly spaced spacings, or did they start small in distance and get further apart? So it's essentially asking you, what did the ticker tape behavior of this ping pong ball look like? It asks you to do some math, including making a graph. I'm going to talk a little bit more about making graphs later on. But as far as pivot goes, and I want to emphasize this, pivot, you will have areas for tables and areas for graphs. And those areas will be linked together. So if you look at this table, and it will be pre-filled out for you, it's already been collected for you. So you have this time in this position. You go down to the graph and you say, well, what is the vertical axis? I want the vertical axis maybe to be time. You're not going to click uncertainty. We do not use the uncertainty in this class. Now put time, and then we have the other column we can put as, I don't know, maybe I put time again. And time versus time, well, that's not what the graph asks for. You're going to have to do a different configuration here. But these are linked directly to these above tables. And there will be another table later on for you to fill out and make a graph. So this is the first part of the lab. I'm going to pause here for a second. If there are questions, go ahead and type them out into chat. I'm going to step off screen and get a drink of water for a second. So we have a little bit more to get through, and then we'll talk a little bit more openly about whatever it is that you guys want to go over. But I am going to bring back up the PowerPoint. And get a little bit deeper into this idea of speed and distance traveled, and define two very important physical quantities. So physical quantities, these are the things that we can measure. And so far, These have all been like direct measurements, we would call them. Why is that? That's because you could directly measure distance, directly measure time. But there's an important physical quantity called speed and velocity, and these are two things that seem very similar to each other. They seem very similar to each other, but there's a subtle difference here. We define speed as being the distance traveled divided by time, and velocity to be the displacement divided by time. And as a refresher, distance is the total ground that was covered between start and end. So if we were to have started, let me bring up my annotations again. If we were to have started in this top left corner and gone through this motion, we would have traveled 4 meters to the right, 2 meters down, 4 meters to the left, 2 meters up. We would have gone through a total here of 12 meters of travel. So we would say this is 12 meters distance covered. And let's say that this happened in a time of 2 seconds. Say it took 2 total seconds for it to undergo this whole motion. If it were to have taken 2 seconds, it would be 12 meters divided by 2 seconds. This would be 6 meters per second. And again, we have a measurement here. It's a measurement that includes a number, 6, and a unit, meter per second, right? Meter per second is a unit for speed. It tells you how quickly you are going. But if we think about displacement, here's where things get a little bit interesting, because displacement was defined to be how far out of place you are, meaning how far from where you began are you located. And if we look here, we have that green circle representing our starting location after our motion. We are where that red circle is, right? We go 4 meters to the right, 2 meters down, 4 meters left, 2 meters up. Our starting location and our ending location, well, it's the exact same location. We are not out of place at all here. So our displacement here ends up being 0 meters. And the time, well, the time was 2 seconds, right? But 0 divided by 2 is still 0, and then unit meter per second. So our measurement here has a number 0, our velocity has a number 0, and a unit meter per second. Now this is interesting. We ended up with 0 velocity. But 6 meters per second for the speed. And this is something that might be a little bit confusing, but the reason why is because we say with velocity, direction matters here. Direction matters. And I'll explain what I mean by that in a second. But to say direction matters is an important quality of this velocity. So when we look at this, we say we have a velocity that moves us to the right 4 meters, but also in our path, we have a velocity that moves us to the left 4 meters. So the direction here tells us 4 meters to the right, 4 meters to the left. We have opposing motions here. And since they are opposite in their direction, we might say that they cancel out. So we say 4 meters to the right cancels out the 4 meters to the left. And when we look at the up and down motion, 2 meters down cancels 2 meters up. They are exactly opposite in their motion. Now, this is something that's going to take a little time to get used to. But we have this idea that they are opposite, so they cancel out. So while the speed is 6 meters per second, that tells you how fast you're traveling at any moment in time. Your velocity has direction, and that might lead it to having some cancellation, and that's okay. That's okay that it cancels out. It's okay that you get 0 meters per second. Because all I would tell you is that during the motion, you ended up at the same place you started. Putting this idea, though, of speed being distance over time and velocity being displacement over time, putting those into practice, we can start to have analysis of motion that we do graphically. So I'm going to show you first example of motion. Now, if we look at the bottom here, we have a car. Our car is this little red car right here. We see that it moves 10 meters in 1 second, another 10 meters in the next second, another 10 meters in the next second. If this were a ticker tape drawing, we would have markings such as that these green markings I'm making, we have green marking, green marking, green marking. We see that they're all equidistant, meaning they're not spreading out, they're not getting closer together. That tells us we have constant velocity motion or unchanging speed. We are not accelerating. Remember, that's what them being equidistant means. So we have this motion of this cart moving from left to right, and we can graph out the motion. We can graph out position versus time. If you remember on that exercise in the first part of the pivot activity, it asks you to create one of these graphs. But we graph out the motion versus time. We say, okay, 0 seconds, we're at 0 meters. At 1 second, we are at 10 meters. So we have a point right there. 2 meters, we're at 20, 3 meters at 30, and we start to see that this forms a straight line. And this is always going to be true, coincidentally, is that if your object doesn't speed up and it doesn't slow down, then it will form a straight line when you graph the position versus the time. And with this straight line, well, there's a quality of lines that we can look at. We can look at the steepness of that line, and that would tell us something. I'm going to show you an example of this in a second. But it would show us something if we had an understanding of the steepness of this line. And let's see if we can determine what the steepness, or in mathematical terms, what the slope of the line represents. So here I have a GIF that is going to play, and we see the blue car moving and the red car moving, and these are graphs of their various positions versus time. Now, the red car comes on screen at 4 seconds. That's why you don't have any data for prior to 4 seconds. The blue car is always on screen. And we see something. Well, the red car has a line that is much steeper than the blue. In other words, it has a larger slope when compared to the blue car. And when we look at the actual motion of the cars up top, well, the red car is very clearly traveling faster than the blue car. And this is the link between the velocity, how quick motion is happening of an object, and the representation on a graph, is that the faster car seems to have the larger slope. And we generally would say that a small slope on position versus time indicates slower motion. And as that slope goes up, well, the velocity increases in case of faster object. So there's a connection here between the slope and the velocity. And this next slide is going to be a little bit of a mathematical review. So in this next slide, we're going to talk about how to calculate out that slope value. So looking at our car, we travel 10 meters every second. We graph out the motion, and it gives us a straight line. We just did this. And we want to know what the slope is. Well, to find the slope, what we're going to do is use the rise over run equation for a line. And that tells you that the slope those two things are related by the slope. The slope is the rise divided by the run. This is the mathematical definition for slope. If we look at this, our green line starts at 10 and goes up to 30. So we have a total rise of 20 meters. If we look at the run, we start at 1 and we go to 3 in this case. that is a change in 2, right? 3 minus 2 is, or 3 minus 1 is 2. That gives you 10 meters per second. Well, 10 meters per second, where have we seen that before? That was our speed of this car. It travels 10 meters every second. That is the speed of this red car, 10 meters every second. So the slope, not only does it tell us the steeper the slope, the faster it is, there's actually a connection numerically in that when you calculate out the slope, you would get this value for the slope, and that value is the velocity of the car, or the velocity of whatever object it is you're looking at. And to further our mathematical review of lines, I want to take one step even further back. What happens if you're not given a graph, but you're asked to make a graph? And again, this week in your lab, you will be asked to make a graph. And you will want to make a graph of position on the vertical axis and time on the horizontal. All right. When we look at this, we say our time goes 0 to 4. So I'm going to make markings on here 0, 1, 2, 3, 4. And then we can even go on, maybe make 5, 6, I don't know. And all of these is time in seconds. So it's 1 second, 2 seconds. I'm not going to put the S on each of those just to save a little bit of time on the drawing aspect of it. And then our vertical positions, we might start at 0, 6, 12. The exact scaling will be done for you by the computer. I'll show you where this is in the activity momentarily. But you might create a graph for your objects. If we were to mark out the motions, we see 0, 0 is a point. So we put it at 0.00, and 1, 6, and 2, 12 is our third point. That was a little bit off. And then we have 3, 18, and then 4, 24. So to make a graph, you set up your scales, you put your data points on there, and what do you know? It forms a straight line. And I wish I were better at drawing straight lines with my mouses right now, but you get a straight line. You have your straight line. And with your straight line, you can look at two things. You can look at where does it cross the y-axis at 0, 0. In your graph this week, you should have something that has 0 for the y-intercept. That just tells you that it starts at 0. The other thing you can look at here is and I'll use pink for this, the slope, which would be rise over run. In this case, I'll look at these two data points. Our run will be from 1 to 3 seconds. That is 2 seconds. Our rise is from 6 to 18. That is 12 meters. So that means your slope, and your slope will actually be calculated for you by the computer. But this is all it's doing, is doing rise over run. And in this case, your slope is going to be 12 meters over 2 seconds. 12 meters over 2 seconds gives you 6 meters per second. So that would be your slope. That tells you how fast you're moving. And in fact, that is true. You move 6 meters every second. This is the same numerical values that I had earlier in the lecture, but this is the graph. Kind of returning back to the pivot activity to give you a rundown, and then we'll open up to whatever questions that you have. I'll probably end the recording pretty soon. I got to get rid of those annotations too. Okay, so the second part of the activity is where all of that numerical values will come into play. So you go through the first activity, has you look at these balls as they go through arrays, make a prediction. Second part of the activity, or second part of the main activity, is going to be analyzing the motion of a bowling ball. Now, everybody should get a randomized video here. So the video you get might be different from the video that someone else gets. So your numbers won't be exactly the same, especially towards the end. But that's kind of the point with the discussion that I have at the end. When we look at this, it's going to be taking measurements of distances. So you break out the ruler and addressing some of the concerns that I heard last time through the discussion board. Yeah, it's tough to make these measurements. You're going to have to really focus and look hard, but ultimately that's true as measurements on a computer or in real life. It can be quite difficult to be accurate, and that's part of it. I do create these activities to give you some leniency, some room for error in your measurements. So if you're off by a couple of centimeters, it shouldn't be the end of the world. But it's true that it's hard to take exact, accurate measures. In fact, you can never be perfectly exact. So the goal is to just give it your best estimation. So I might say in this case, 150 centimeters between where it started and the flag, right? So you have the measurements of distance being taken. You have a measurement for time being taken with the stopwatch. Those are the two measurements that you're going to have to measure your distance and time. And once you move on with the lab, you're going to then take the timer and you're going to measure where the bowling ball is at very specific time intervals. So for example, in this aspect, it says, where's the location of the ball at 0.4 seconds? You look for the frame where it's at 0.4 seconds, and you measure the distance the ball has traveled, well, about 30 centimeters in this case. And then you go through and you fill out the rest of them. Once you have those, you have a bunch of position versus time measurements, just like was the case when we had our, let me go back to the PowerPoint for a second. Just like was the case with our little red car, we have various measurements of positions at certain times. So what we can do is take those positions versus time, put them in a graph. Perhaps we measure that at, I'm just going to put in random values here, at 1 second, 2 second, 3 second, 4 seconds. We're at 3, 6, 9, and 12 centimeters. These are not values that you will have exactly, but you just fill out the graph with the answers you got earlier. Create the graph of position and time, and you are going to get the information for that position and time graph and answer the rest of the questions. So you go through and you analyze the motion of all of these different objects. This activity might take you a little while. Having attended this session, it should make it a little bit easier. You know what to expect as you go throughout the lab. But of course, if you have any questions, let me know. You'll get to the final discussion activity, and with this discussion activity, you are going to paste a copy of your graph into the, sorry, we also want to do curve fits, linear. It describes it up here, what to do there. You're also going to want to do curve fit linear. So in the discussion post, you're going to put a picture of your graph as well as the information with the slope and the y-intercept. And you're going to compare your graph to some of your classmates. Again, everyone has different videos assigned to them, so we should have a wide variety of videos for you guys to compare to each other. There shouldn't be too many that are the exact same. All right, and that'll take you through the end of the lab. At this point, I'm going to stop the recording if there are no questions, and then we'll do sort of more informal office hours off recording. All right, let me go ahead, stop share.